All right, hello everybody and welcome to the Unit 13 review session. This is our unit that first deals with gas laws. First off, the format of your test is going to be 5 multiple choice questions, and then you will have 8 free response questions. All right, just so you know, of these 5 multiple choice questions, you are responsible for knowing the different gas laws and the names that go along with them. Okay, all right, so just to review a little bit as far as some things that I always put right away on my paper is I would definitely want to put this one. So V1 P1 T2 is equal to V2 P2 T1. As we know, that is the combined gas law. This combines Boyle's, Charles, and Gay-Lussac's law all together. And we're going to use this in a lot of the different problems that we come across. So let's go on ahead and jump right into these problems. Number 1, a glass cylinder has a volume of 105 mils. When 2 grams of nitrogen gas at a temperature of 175 degrees Celsius and a pressure of 650 millimeters of mercury is heated to 280 degrees, what is the new pressure of the gas? So a couple things about this. I've given you a glass cylinder and it has a volume. Well, a glass cylinder does not expand or contract, all right? And if you notice from this problem, I don't talk about volume again. So this is information you actually do not need. We're not going to be dealing with volume in this problem. Then I tell you a mass. I tell you how much of this gas. Well, nowhere in this unit did we discuss mass, so this 2 grams is also information that you do not need. What you do need to know is that you have a gas that has a temperature of 175 and a pressure of 650, all right, mmHgs. All right, and you have changed the temperature. So we are dealing with pressure and temperature here. So this is the gas law that we're going to be using. P1 T2 is equal to P2 T1. All right, if this was a multiple choice question and I was asking you which gas law deals directly with pressure and temperature while leaving volume alone, that is Gay-Lussac's law. That would be this one. All right, so now let's go on ahead and solve for this. I like to do my algebra first, but it's really up to you. You just have to make sure that you show work. We are looking for new pressure, so we are looking for P2. So I'm going to divide each side by T1. So P2 is going to be equal to P1 T2 over T1. All right, I'm now going to go ahead and put my numbers in. I have an initial pressure of 650 mmHgs. All right, now with temperature, please remember, because this is going to come up in a lot of our problems, you must convert these Celsius temperatures to Kelvin. All right, anytime when dealing with gas laws and we're dealing with temperature, you must convert to Kelvin. So this is T2. This is our final temperature, which is 280 degrees Celsius. 280 plus 273 gives us 553 Kelvin. Our initial temperature was 175. 175 plus 273 gives us 448 Kelvin. All right. Our kelvins divide out. We're going to be getting pressure, we're going to be getting millimeters of mercury, which is a pressure unit, which is good because I'm asking you for pressure. And once you put this into your calculator, and you should practice putting it in your calculator, so feel free to pause me, you should get about 802 millimeters of mercury. Don't stress too much about the rounding. Make sure you're reasonable when it comes to significant figures, and we should be good. All right, let's move on to number 2. An unknown gas diffuses 3.84 times as fast as I2. What is the molecular mass of the unknown gas? So we're talking about diffusion problems. With diffusion problems, we are going to be dealing with Graham's law. So with Graham's law, remember we have V1 over V2 is equal to the square root of M2 over M1. All right, this V1 over V2 is the rate of diffusion. It's called the relative rate of diffusion. All right. Okay. All right. And that is this number, 3.84. All right. So we're going to have 3.84 is equal to the square root. Now, I'm telling you here that your unknown gas diffuses 3.84 times as fast as I2. Please remember that the lighter the gas, and by light I mean by molecular mass, the lighter the gas, the faster it is. So we're looking for a gas that is lighter than I2. All right, so M1, because I said the unknown gas is doing this, that is your unknown gas. So that is X. All right. That's what we're looking for. The molecular mass of 2, our second gas, is iodine. So you're going to look in your periodic table. You're going to find the mass of iodine. You're going to multiply that by 2 because it is I2. Iodine is diatomic. And you should get 253.8 as the molecular mass of iodine. Okay. You're then going to, all right, in order to get rid of that square root, you're going to square each side, which ends up giving you 14.7 is equal to 253.8 over X. You solve for X and you get about 17.3. Now, ask yourself if that makes sense. We said that this gas was going to be lighter than iodine. Is 17.3 lighter than 253? It certainly is. We're looking for molecular mass here. You could answer this in AMUs, or you could go grams per mole or atomic mass units. I would accept either one on a test. All right, but always remember that the lighter the gas, the faster it is going to move. Okay, so let's take a look now. Let's move on and take a look at number 3. Okay. Number 3, a student collects 555 mils of nitrogen gas over water. Right there, you see over water. You should think, oh, okay, this is going to have a Dalton's Law problem in it. All right, it's not completely Dalton's Law, but it's going to have Dalton in it. At 40 degrees and 121 kPa, what volume will the dry gas occupy at STP? The vapor pressure of water at 40 is 5.2. All right, so let's get back to this Dalton's portion. If I tell you it's collected over water and then I give you a pressure, all right, that 121 kPa is the pressure of your dry gas and your water vapor. All right, so you have to take that 121 and you're going to subtract 5.2 from it because 5.2 is the water vapor. I'll always give you the water vapor pressure. That's not something you have to remember. All right, but you're going to take 121 and subtract 5.2, which gives us 115.8 kPa. That becomes your initial pressure. All right, I wrote a little big here, but that's okay. I can still fit it. Now that you have that, realize you're not going to use this 121 anymore. You're going to use that 115. You have a volume of your gas. You now have a pressure of 115. All right, so we'll go ahead and write it out this way. Some people like to do this. Your initial pressure is now 115.8. Your initial volume is 555 mils. All right. If you notice here, you're at 40 degrees at the beginning and you're at 40 degrees, so it's at 40 degrees, so that's your initial temperature, excuse me. So T1 is 40 degrees Celsius. All right, so 40 degrees Celsius, we're gonna convert that, as always, to Kelvin. So that's 313 is Kelvin. All right, you are looking for, let's get to the 2's. You're looking for your final volume. So V2 is our question mark. Your final pressure, you're at STP. STP stands for standard temperature and pressure. So your new pressure is standard. We're in kPa, so that's 101.3 kPa. And your standard temperature is 0 degrees Celsius, so that is 273 Kelvin. All right, you're dealing with all 3 variables, so this is a combined gas law problem. And because I've used so much space, I'm going to get a blank piece of paper here to finish this up. All right, so again, combined gas law, V1 P1 T2 is equal to V2 P2 T1. We are looking for final volume, so V2 is going to be equal to V1 P1 T2 over P2 T1, just plugging in my numbers now. And when I do that, I have 115.8 kPa times your initial pressure. That's your pressure times your initial volume of 555 mils. Remember, it doesn't matter what order you do those. T2 though, here's 273. Your final pressure is standard, 101.3 kPa. All right, and your initial temperature is 313. Kelvin. Okay, and then when you solve for that, take a second, put that into your calculator, and when you solve for this, you should get about 553 mils as your final answer to number 3. Okay, all right, so let's move over to number 4. Let's take a look. Describe the relative rate of diffusion for carbon monoxide and butane. All right, when I say to describe, you do have to answer this in a sentence, but first you have to do the math to do it. So obviously first you need to know what these two are. So carbon monoxide is CO. Butane from our organic unit, all right, but is 4, so, and it is just a simple alkane, so C4H10. Okay. When you find the masses of these, all right, you will see that butane has a molecular mass of 58 and carbon monoxide has a molecular mass of 28. All right, so you know which one's going to be faster. Carbon monoxide is going to be faster. We just want to see how much faster. So V1 over V2 is equal to the square root of M2 over M1. All right, we're looking for this all together as a number. Your M1 is carbon monoxide. All right, and that's going to be 28 on the bottom there. 58 is going to go on the top. That is your M2. And when you solve for this, you get about 1.44. Now be careful. I asked you to describe, so now you have to describe it. All you have to do, carbon monoxide diffuses 1.44 times as fast as C4H10, or you could certainly use the words carbon monoxide and the word butane. Either one is fine. But this is what we are looking for our final answer when we ask you to describe. Okay. All right, now let's take a look at our last 2 problems for the review session today. Number 5, you have 145 mils of gas at 350 millimeters of mercury and negative 20 degrees Celsius. Correct the volume to what it would be at STP. All right, so again, we are changing volume and pressure and temperature. So again, we're doing combined gas. V1, P1, T2 is V2, P2, T1. Write it out as many times as you can. It will help you remember it. All right, we are changing. The word correct just means to change. We are, again, looking for the V2 again. All right, we've done this a couple times. And V2, as we know, is P1, P1, V1, T2 over our P2, T1. Okay, this is a pretty straightforward problem, not a whole lot to it. All right, so you have 350 mmHgs times 145 mils times your final temperature, which is standard. Remember STP, so that's 273 Kelvin. All right, our final pressure, which is standard, is 760 mmHg. Make sure that you remember all of those standard values, all right, because they will come back. And then negative 20 is your initial temperature. Negative 20 plus 273 is 253 Kelvin. All right, when you solve for this, you should get about 72.1 mils as your final volume. All right. Last up, a balloon with a volume of 622 milliliters at 2.5 atmosphere and 30 degrees Celsius is compressed to a volume of 400 mils and a pressure of 5 atmospheres. What is the temperature in Celsius inside the balloon? All right, so again, which gas law? You're dealing with volume, you're dealing with pressure, you're dealing with temperature. We're going to be using that combined again. What is the temperature? So you are looking now for T2. That is the variable you're going to be looking for. Well, T2 is going to be P2, V2, T1 over P1, V1. All right. I just used my equation here, my combined gas law, looking for T2. So I'm going to divide each side by V1, P1. Okay. Now, this question can be a little confusing because I asked for the final temperature in Celsius. You still must convert to Kelvin to do the problem. Then you will convert back to Celsius at the end. Please make sure you remember all gas law calculations must be done in Kelvin temperature. So your final pressure here is 5.0 atmospheres. All right, your final volume is 400 mils. Okay. Your initial temperature is 30 degrees Celsius, which changing to Kelvin is 303 Kelvin. Your initial pressure is 2.5 atmospheres. Your initial volume is 622 mils. Okay. When you solve for T2, you get an answer of 390 Kelvin, which is great, and that means you did it right. However, you do have to now convert that to Celsius because that is what I asked for in the problem. All right, so remember to go from Kelvin to Celsius. You're just going to subtract 273, which gives you a final answer of 117 degrees Celsius. Okay. All right, everybody, good luck on your test. Again, make sure you're writing out all of your work. Make sure you're reading the problem carefully, and make sure you are converting those temperatures to Kelvin. All right, take care. Bye-bye.